Now, in the last 1 or 2 weeks, we got to know the Lagrange formalism, which is an alternative way of formulating classical mechanics, an alternative to Newtonian mechanics. And the motivation for the Lagrange formalism was mainly practical. We saw the Lagrange formalism has 2 major advantages over the Newtonian formulation. It's straightforward to incorporate constraints on the system, and it's very easy to go to different coordinates. Often it's convenient to treat a problem, say, in spherical coordinates or cylindrical coordinates or some other curvilinear coordinates which are not Cartesian. And the Lagrange formalism allows you to do that, and to transform from one coordinate system to the other in a very easy and straightforward manner. Today we're going to start yet another framework for classical mechanics, which is the Hamiltonian formulation of classical mechanics. And here the motivation is not so much practical. You will, in most cases, you won't gain much in terms of practical calculations, but the Hamiltonian formalism is extremely interesting and important conceptually, because it's an important bridge towards quantum mechanics on the one side and statistical mechanics on the other side. It's of course a bit early to explain that to you because you're at the beginning of the theory course, so you haven't had these other subjects yet. But very soon you will learn, next semester you will learn about quantum mechanics, and very soon you will see the connection between the Hamiltonian formulation of classical mechanics and quantum mechanics. Hamiltonian mechanics plays in a new arena, in a new kind of space, which is phase space, called phase space. Both so the Newtonian and the Lagrangian formulation of classical mechanics, they lived in configuration space. So we looked at systems, say, with a certain number of degrees of freedom, say a single particle with 3 degrees of freedom, and then we described that in 3-dimensional space. Now that's called the configuration space. Hamiltonian mechanics lives in a space that has twice that dimension. So for a single particle, that would be a 6-dimensional space, which is called phase space. And as a first topic, I'd like to explain to you how a phase space is defined and what it means. Let's recall from last week, the definition of the generalized momentum. The generalized momentum was defined, and I leave the space on purpose, as the partial derivative of the Lagrange function with respect to the velocity. And this holds for when we have a system with f degrees of freedom, then this holds for all f components, all f coordinates we have associated generalized momenta. Now the Lagrange function depends in general on the generalized coordinates, the generalized velocities, and possibly explicitly time. So the generalized momentum is defined in this way, and the Lagrange function is a function of the generalized coordinates, velocities, and time. And accordingly, if we write it like that, we get the generalized momentum as a function of coordinates, velocities, and time. So we have momentum as a function of coordinates, velocities, and time. We can solve that for the velocities. say for qi dot. And then we get the velocity component, qi dot, as a function of coordinates, momenta, and time. And now, previously, we always said that the state of a system, of a mechanical system, is uniquely characterized by all the positions and all the velocities. You remember from the very beginning, our principle of determinacy, it said if we know of a mechanical system, we know all the positions and all the velocities, then by way of the equation of motion, we can predict, we can calculate the state of the system at all future times. Yeah? So initial conditions are completely specified by initial positions and initial velocities. Now, using this relationship between momentum and velocities, we can replace the velocities by the momenta. And we can say the state of a system is characterized by all the positions and all the momenta of all the particles involved. And we can say, as initial conditions, we specify all the positions and all the momenta. Right? So the idea is that we characterize the state of our mechanical system no longer by positions and velocities, but now by positions and momenta. In particular, the initial conditions are now given as initial positions and momenta rather than initial positions and velocities. Then what we can say is that the state of a mechanical system is a point in a 2f dimensional space. And the coordinates in that space are the f position coordinates, the qi's, and the f pi's, so the f momentum coordinates. So with this description, the state becomes a point in a 2f dimensional space with the coordinates qi and pk. And this space is called phase space. So in the simplest case of a one-dimensional system, we have only one position component and one component for the momentum, and then the phase space is a two-dimensional space which has as coordinates q and p. We can specify the initial conditions by giving the initial position and the initial momentum. And once we know these initial conditions, then with the help of the equation of motion, we can predict the further evolution of the system, and we get a trajectory in phase space which tells us the position as a function of time and the momentum as a function of time. So this is the basic idea behind phase space. Then remember that already in the Lagrange formalism, we introduced the so-called Hamilton function. The Hamilton function was defined as sum over I, qi dot pi minus the Lagrange function. That was the definition of the Hamilton function. In the previous Lagrangian framework, the Hamilton function was a function of positions, velocities, and possibly explicitly time, because pi, in turn, that appears in this definition, the pi is expressed in terms of q, q dot, and t. So this makes the Hamilton function a function of q, q dot, and t. But we can also write the Hamilton function now as a function on phase space. So we can write it as a function of q, momentum and time, position, momentum and time, if we express the velocity, qi dot, if we express that as a function of position, momentum and time, and the Lagrange function, that was, we always had the Lagrange function as a function of q dot and t, but here too we do this transformation and we say we express q dot, the velocities, in terms of position, momentum and time, and then we still have explicitly time. So with these substitutions we can express the Hamilton function as a function of the positions, the momenta and time. And in this way the Hamilton function becomes a function on phase space. To make this a bit more concrete, let's look at a specific example. Let's look at a free particle in 2 dimensions. And to make it a little bit more interesting, we do that not in Cartesian coordinates, but we describe that in polar coordinates. So we take, if the particle is here, then we describe its position by polar coordinates r and phi. Obviously the transformation law is x is equal to r times cosine phi, y is r times sine phi. We can write the kinetic energy in Cartesian coordinates as before, as we know. Now if we use the coordinate transformation that I wrote on the right hand side, you can express that in polar coordinates. You find this is m half r dot squared plus r squared phi dot squared. The Lagrange function is t minus u, but we have no potential energy here, it's a free particle, so this is simply equal to t. Now we want to go to the Hamilton formalism. For that purpose, we first need the momenta. Let's look at the generalized momentum associated with the radial coordinate. That's the partial of the Lagrangian with respect to r dot. When you use the kinetic energy above, take the partial derivative, you find this is mass times r dot. And you can solve that for the velocity. You can, rather than expressing the momentum in terms of the velocity, you can express the velocity in terms of the momentum. You say r dot is 1 over m times the momentum pr. Likewise for the angular coordinate, you can calculate the associated momentum p phi. This is partial L over phi dot. And this is with the formula above, this is mass times r squared times phi dot. And again, you can solve that for phi dot, and you can express the velocity component phi dot in terms of the associated momentum. This is p phi over mr squared. Now we are ready to calculate the Hamilton function as a function on phase space. So as a function of the coordinates r and phi and the momenta pr and p phi. Now this is by definition velocity times momentum. We take both components, sum over all components, and here we have the radial and the angular component, minus the Lagrange function. Now we express the velocities in terms of the momenta. So r dot, we write PR over m. So this gives us PR squared over m, first term. The second term, there too we express phi dot in terms of the momentum, the formula above. So we obtain p phi squared over mr squared. From this we subtract the Lagrange function. The Lagrange function equals the kinetic energy, which we have above, but it's expressed in terms of velocities. So there too we have to eliminate the velocities and express them in terms of momenta. So in the formulas up there, we also replaced r dot by PR over m and phi dot by p phi over mr squared. And what we find is, for the first contribution, we have mass over 2 in front, and then we have PR squared over m squared, and then the second contribution, we have mass over 2, and then we have r squared times phi dot squared. This gives in total p phi squared over m squared r squared. Now here, first of all, you can eliminate one of the m's, and then you see the first of these two terms that you subtract. That's PR squared over 2m. That's just half of the first term. So you can eliminate this altogether and replace this and add a 2 in the denominator. And likewise for the last term that you subtract, that's just half the term that you have before. So you can eliminate this one here and write a 2 in the denominator. And now this looks already quite familiar to you. You know the kinetic energy in Cartesian coordinates is given by p squared over 2m. And what you have here looks very much like p squared over 2m, the kinetic energy as it should be, because here we have a time-independent coordinate transformation. Therefore, the Hamilton function physically is the total energy. Since we don't have a potential energy, the Hamilton function must be the kinetic energy. So in Cartesian coordinates, it ought to be p squared over 2m. And this is very similar to what we have here, only that it's expressed in polar coordinates, so the angular contribution looks slightly different, but physically it's the p squared over 2m. So let me just quickly summarize the basic idea. When we go from Lagrange to Hamilton, we go from configuration space to phase space. We eliminate the velocities in favor of the momenta. So we write, in particular, we write the Hamilton function no longer as a function of positions, velocities, but we write it as a function of positions and momenta. So that the Hamilton function becomes a function on phase space, which has coordinates q and p. Now that we have the Hamilton function as a function on phase space, let us take partial derivatives of the Hamilton function with respect to all the variables on which it depends. And let us start with the partial derivative of the Hamilton function with respect to a certain coordinate qk. And when I write it in this way, in the Hamiltonian framework, I mean that the Hamilton function is a function of the q's and the p's. And when I take the partial derivative with respect to a specific qk, then I keep all the other variables fixed in this partial differentiation. So I keep all the other qi's fixed, and I keep the momenta fixed. Let me write this explicitly because it's important. So keeping all other qi different from k, and all pi fixed. Yeah, and the important point here is it's the whole derivation, the calculation that we're going to do only works if you consider the Hamilton function as a function on phase space, as a function of momenta, and not a function of velocities. Yeah? So this is important, to keep the pi's fixed. Let's use the definition of the Hamilton function. It's the sum over I qi dot pi, when we take the partial derivative with respect to qk, we get a contribution partial qi dot with respect to qk. And here, to be really clear, I want to write explicitly that you keep all the other q's and all the p's constant. So this little index or this little subscript next to the bracket means that when we take the partial, those are the variables that we keep fixed. Well, times pi. Then according to the product rule, we would have another contribution qi dot and then the partial of pi with respect to qk, keeping the p's fixed. But this is of course 0. Yeah? When I take the derivative of p while I keep p fixed, then of course it's 0. So it doesn't contribute. This is the only one. And then we have the, in the definition of the Hamilton function, we have minus the Lagrange function. And from that we get a contribution partial L with respect to qk, keeping all the other q's and p fixed. All right, here a word of caution, because you might say, well, the partial derivative dl over dq, that's what appears in the Lagrangian equation of motion. Remember, the Euler-Lagrange equation said d over dt, dl over dq dot, on the left-hand side, equals partial dl over dq on the right-hand side. So you might be tempted here to use the Euler-Lagrange equation for dl over dq. But in the Euler-Lagrange equation, the Lagrange function is considered a function of positions and velocities. So in the Euler-Lagrange equation, when you take the partial derivative of L with respect to Q, you keep the velocities fixed. But here, you keep the momenta fixed. So these are two different partial derivatives, and you're not allowed to use here the Euler-Lagrange equation. We must consider carefully what this partial derivative is. And to do that, let me make a little side calculation. Let me look at the differential, the total differential of the Lagrange function. When we consider the Lagrange function as a function of positions and velocities, then we can write this total differential in this way. We can write it as, and now for simplicity I would like to omit the indices and the sums, or just write it in the one-dimensional case. We can write this as partial L over partial Q dq plus partial L over partial Q dot dq dot. Then we can say, but here we want to have everything as a function of positions and momenta. So somehow we have to manage to transform this dq dot into dp and possibly dq. So only differentials of position and momenta should appear rather than velocities. So how do we do that? We can say the dq dot, in turn, we can now consider the velocities as a function of positions and momenta. So we can express the differential of velocity, dq dot, can write it as partial q dot over partial q, and now I make explicit at fixed p dq plus partial q dot partial p at fixed q dp. Okay. Maybe here I should, to make this distinction really clear, also make explicit what is kept constant. Here you keep q dot constant, and here you keep q constant. When we insert this expression for the differential of q dot up here, we find this is partial L over partial Q at fixed Q dot times dQ. And then we have from the second term, we have a contribution partial L over partial Q dot at fixed Q times partial Q dot over partial Q at fixed P dQ. Plus partial L, partial Q dot at fixed Q, partial Q dot, partial P at fixed Q, dP. So we start from the total differential of the Lagrangian, express it in terms of dQ and dQ dot, then we express dQ dot in terms of dQ and dP, put it in there, and we get the total differential of the Lagrangian dl in terms of dq and dp. What's in front of the dq? This here. This is now the partial of L with respect to q at fixed p. And that's what we were looking for. And what's in front here? This is the partial of L with respect to p at fixed q. This result we can insert in the first line. There we have the partial. We seek the Lagrangian, the partial of the Lagrangian with respect to qk at fixed all other q's and fixed momenta. And this is precisely what we have in the bottom line. The first bracket, the square bracket, this is precisely the expression we were looking for. So we insert it up there. We have still the first term, sum over I, dqi dot dqk at fixed other q and p times pi minus. And then I made the side calculation without components and without the sum. I did that in the one-dimensional case. If you allow me, I would now like to go back to the case of arbitrary dimension. So we have then dl over dqk at fixed other q and q dot. And then we have sum over I dl over dqi dot at fixed q times partial dqi dot over dqk at fixed q and p. For arbitrary dimensions, let me just quickly repeat that. So we have the total differential of the Lagrange function. For arbitrary dimensions, we have sum over I partial L partial qi dqi. This is at fixed q dot plus sum over I partial dl dqi dot at fixed q dqi dot. Then we say this dqi dot, we express that differential now in terms of q, differentials of q and p. So we say this is the sum over all k, let's say, dqi dot partial dqk at fixed p dqk plus sum over k dqi dot dpk at fixed q dpk. Now inserting this above, we find this is sum over I partial L partial dqi at fixed q dot dqi plus, and then we have sum over I and sum over k dl over dqi dot at fixed q times partial qi dot partial qk at fixed p dqk. And then we have a contribution plus sum over ik dl dqi dot at fixed q times partial qi dot partial pk at fixed q dpk. Now we simply inserted the expression for the differential dqi dot into the first line, and now we have a new expression for the differential dl of the Lagrange function. Now I would like to take together the first two contributions, those that have the dq, and treat separately the one with the dp. To do that, first of all, I'd like to change indices. In the first term, rather than sum over I would like to have a sum over k. I have a sum over k, so that I also get dqk in the first term. Right? So then I would like to bring that together with the second term, and then for both we have at the end dqk. And in the square bracket we have the contribution from the first term, which is the partial L partial qk at fixed q dot. That's the contribution from the first term. And then from the second term we have another sum over I, and then we have dl partial qi dot at fixed q times the partial qi dot qk at fixed p. So in this way I have grouped together the first two sums where the dq appears. And then we are left with the sum with the term with the dp, so partial L qi dot q, partial qi dot pk at fixed q dpk. Is that fine with you up to here? No, it's a bit tedious, but I think it's good that you asked me to explain that in more detail, because I realized that there was too much of a leap of faith. Now, what we have in here, this square bracket, this we can identify. I mean, at the same time, if we say the Lagrangian, if we view that as a function of q and p, then we should have, for the total differential, we should have, that's the sum over k, partial L over partial qk at fixed p dqk plus sum over k partial L partial pk at fixed q dpk. When we compare that, we can identify the square bracket with the partial L over q at fixed momentum, and we can, in the second sum, if we write that as two separate sums, then we can identify this here with the partial of L over P at fixed Q. This is what we have for the partial of L over QK at fixed momentum. And this is what I would like to use, or what I already did use on this page here. In the first line, the term on the right, the partial of L with respect to Q at fixed momentum, I expressed that with the help of the result of the other page, and we get the result in the last line. Do you recognize what this is here? The term with the blue underbrace, what is that? The partial derivative of the Lagrange function with respect to q dot at fixed q. That's the generalized momentum by definition. This is pi. This means that this sum, this last sum that we have here, becomes the sum over I pi times this partial q dot over qk. And that's exactly the same expression that we have in front. You see, the first sum is also the sum pi partial qi dot qk. So these two terms cancel. Next question, what is this partial here? It's the partial of the Lagrange function with respect to qk at fixed velocities. Here, now this is Euler-Lagrange equation, because in the Euler-Lagrange equation we consider q and q dot as independent variables. Yeah? And therefore, this is, by Euler-Lagrange, this is d over dt partial L qk dot. But this is nothing but, because in the bracket, that's the generalized momentum again. And then we have a d over dt in front. This is the time derivative of the momentum. That's pk dot. So at the end of this calculation, we find that the partial derivative of the Hamilton function with respect to position, with respect to qk, is nothing but minus pk dot. Then we can move on to another partial derivative of the Hamilton function, namely with respect to a momentum component. So next I would like to consider the partial derivative of the Hamilton function with respect to pk. And again, as before, I consider the Hamilton function as a function on phase space, therefore a function of the q's and the p's. And when I write this partial derivative, then I imply that I keep all other pi's, so for I different from k, and all the q's fixed. We proceed in the same way as before. We remember the definition of the Hamilton function. We have sum over I, qi dot pi. We take the derivative with respect to pk. So we have two contributions. We have the partial qi dot with respect to pk at fixed q's. And I don't write explicitly, but I imply that when I take the partial with respect to a specific pk, that I keep all the other pi's fixed. What I do write explicitly is that I keep the q's fixed, all the q's, times pi. Then, product rule, we have a contribution qi dot partial pi with respect to pk at fixed q's. And then we have minus the Lagrangian, which we have to derive partially with respect to pk at fixed all other pi's and q. Let's start with the last term, partial dl over dpk at fixed q. We find that on the previous page. That's the second under brace. Yeah. Now you have from the last line, in front of the dpk, you have the partial of L with respect to pk at fixed q. That's what we are looking for. We can identify that with the expression in front of the dpk on the line above. That is this sum here, right? So we can replace the partial of the Lagrange function by this expression here. What is this term here that I underlined in blue? Partial of L with respect to velocity at fixed q. Generalized momentum, by definition. So this is pi. Now compare this sum with the first sum that we have in the first line. It's exactly the same, and these two cancel. So this sum here and that sum are exactly the same, and they cancel. And we are left with this expression in the middle. What is this partial here? Partial pi with respect to pk at fixed q's and fixed all other p's except pk. If k is different from I, then it's 0. If k is equal to I, then it's 1. So it's the, and one writes that in a compact way as a Kronecker delta. So then what we are left with, the sum over I, qi dot, and then the Kronecker delta ik. This means we can simply execute the sum over all I, and what remains is qk dot. So we find the partial derivative of the Hamilton function with respect to pk is qk dot. That's getting nice, I think, because before we had partial of h with respect to q is minus p dot, and partial of h with respect to p is q dot. Last, we should consider the possibility that the Hamilton function depends explicitly on time. If it does, then we can also take the partial derivative of the Hamilton function with respect to time. So this is going to be the last partial derivative that we will consider. So we are looking at partial h with respect to time. But here let me write explicitly that we keep all the q's and all the p's fixed. So it's only the explicit time dependence that matters here. Once again, we start from the definition of the Hamilton function. So we have qi dot pi, chain rule. So we have one contribution partial qi dot over t times pi. We have a contribution qi dot partial pi with respect to t. And then we have minus the partial L with respect to t at fixed q and p. Now one of these terms we can immediately forget, namely the one in the middle, where we have the partial derivative of pi with respect to t at fixed p, amongst others. So we keep p fixed, then of course it doesn't vary, and this here is equal to 0. Then this term here, the partial of the Lagrangian with respect to time t, we have to do an exercise completely analogous to what we did before. We have to translate this into a partial derivative of L with respect to t at fixed q and q dot rather than fixed q and p. And the argument is completely analogous to the previous argument. And you can show, it would be a good exercise for you to do that this is equal to the partial dl over dt at fixed q and q dot plus sum over I partial L over qi dot at fixed q, and then the partial qi dot over t. Once again, terms cancel, because this expression here that I underbraced in green, that's once again, by definition, the generalized momentum, pi. So we have there a sum over I, pi, and then the partial qi dot dt, which is exactly the same as the first term that we have on the first line. I should add, I forgot that this here is at fixed q and p. So this term is exactly equal to that term, and these two terms cancel. The only term that survives is the partial of the Lagrangian with respect to time at fixed q and q dot. But this is something that we encountered before. The partial derivative of the Lagrange function with respect to time up to a sign equals the total time derivative of the Hamiltonian. So this equals the total time derivative dh over dt. So this is the last of the results that I wanted to show you about partial derivatives. As for the derivative with respect to time, of the Hamilton function, the partial derivative equals the total time derivative. Now the first two of the three results that we just obtained are known as the Hamilton equations, and they are really the basis for the Hamiltonian formulation of classical mechanics. Let me summarize these two equations. What we found is that qk dot was the partial of the Hamilton function with respect to pk. Pk dot, that was minus the partial derivative of the Hamilton function with respect to qk, and this holds for all k going from 1 to f if you have f degrees of freedom. These so-called Hamilton equations are the equations of motion in the Hamiltonian formalism. Now we have f differential equations for q, and we have f differential equations for p. So in total we have two f differential equations of first order. Now these are two f differential equations of first order for the q's and the p's. Compare this to the Lagrange formalism. In the Lagrange formalism, we had the Euler-Lagrange equation. The Euler-Lagrange equation read d over dt and then the partial dl over qi dot equals partial L over Qi for I going from 1 to f. So there we have f differential equations, but these differential equations are of second order for the Qi of t. And so in the Lagrange formalism, f second order differential equations for Q of t. In the Hamilton formalism, you have 2f first order differential equations for q and p. In both cases, you need 2f initial conditions to specify the evolution of the system. So in both cases, we have 2f initial conditions. As an example, we consider a single particle in an external potential in 3D. So we have 3 dimensions and we have a particle in an external potential, u of r. To make life simple, we will do it in Cartesian coordinates, so we don't bother about curvilinear coordinates. The Lagrange function is given by kinetic energy minus potential energy. The generalized momentum, pi, which in this case, because it's Cartesian, coincides with the physical momentum, pi, that is partial L xi dot. I write xi rather than qi because they are Cartesian. This is equal to mxi dot. And therefore I can express the velocity, r dot, now in vector notation, in terms of the momentum, that's 1 over mass times momentum. This allows us to write the Hamiltonian, or Hamilton function, as a function of positions, momenta, or the position and the momentum of the single particle, and time which in this case doesn't play a role because if the potential is time independent. So remember, this is velocity times momentum, so in vector notation that's r dot scalar product p minus the Lagrange function, which above is given as a function of r dot, which we express in turn as a function of r, p, and t. This is sort of the general relationship. And when we use the specific form of the Lagrangian above, inserted in here, we find that this is equal to 1 over 2m p squared plus the potential energy. That's exactly what you expect. Hamiltonian equals the total mechanical energy. Kinetic energy is p squared over 2m plus potential energy. Now let's look at the Hamilton equations. The Hamilton equations say, first of all, xk dot, the change in time of the position, is given by partial h over pk, and this means in vector notation, if we insert this Hamilton function, this means r dot is equal 1 over m times p. The other part of the Hamilton equations reads pk dot is equal to minus partial h over xk. And this translates into, in vector notation, p dot is minus the gradient of the potential. Now we have this equation and that equation, and these are two first-order differential equations. Compare this to the Lagrange formalism. In the Lagrange formulation, we have d over dt partial L xk dot equals partial L partial xk, which in vector notation translates into mass times acceleration equals minus the gradient of the potential. And what you have here in green, this is now a single, rather than before you had two differential equations, one for r, one for p. Here you have a single differential equation for r only, but it's a second order differential equation. So this illustrates the point that in going from the Lagrange to the Hamilton formalism, you replace second order differential equation by two first order differential equations. Now in this new formulation with the Hamilton equations, I'd like to have a fresh look at conservation laws. And the first conservation law we can formulate follows from the result that we obtained for the time derivative of the Hamilton function. We found that the total time derivative of the Hamilton function equals the partial time derivative of the Hamilton function. That was one of our results. And it implies that if the Hamilton function does not depend explicitly on time, i.e. the partial derivative vanishes, then the Hamilton function is a constant of the motion. Then also its total time derivative vanishes. So if the Hamilton function does not depend explicitly on time, then it's a constant of the motion. Now remember, under certain assumptions which are often satisfied, namely that the coordinate transformation is not time dependent, explicitly time dependent, and the potential is not velocity dependent, then the Hamilton function can be identified with the physical energy, the total mechanical energy. So in that case, the Hamilton function, being a constant of the motion, expresses energy conservation. So remember that if coordinate transformation is time independent, and as a result the kinetic energy has this bilinear form that we discussed, or another expression is it's quadratic in the qi dot, and also the potential energy does not depend on velocities, then we found that the Hamilton function is simply the total mechanical energy. So then if this is justified, then the statement above implies energy conservation. This is the first conservation law that we can formulate for the energy, or more generally for the Hamilton function. Then remember, in the Lagrange formalism we had defined cyclic coordinates. So these are coordinates on which the Lagrange function does not depend, and we saw that as a direct consequence the associated generalized momentum is conserved. And here we have an analogous result. If you look at the equation of motion pk dot, this part of the Hamilton equations is minus the partial of the Hamilton function with respect to qk. This implies that if the Hamilton function does not depend on qk, then the associated generalized momentum is conserved. So it's completely analogous to the Lagrangian case. If the Hamilton function does not depend on qk, then pk is a constant of the motion, and we have momentum conservation.